One last topic in kinetics describing exactly how fast reactions go and monitoring them is half-life. So the half-life of a reaction is the time required for the amount of reactant to decrease by half. So basically, if you start with some amount of reactant, at what point in time or how long will it take for 50% of that reactant to be gone? Our symbol for half-life is this T1/2. So T and then a little subscript 1/2. So if we have half-life, it's kind of, this is an amount of time that lets us kind of use shorthand to describe the speed of a reaction. So something with a really short half-life is very fast. A reaction with a short half-life is very fast. So this is kind of a number that we can use. So rate constants can be used to quantify speed, but it's kind of awkward and it's hard to think about, whereas half-life, it's a quantity time. Short times mean fast things. And so when you have half-life, one of the things you'll note, it's half of what you had. And so the initial amount is going to be that A with the 0. When we're talking about the half-life, is at the half-life, you will have half of that. So take that amount, divide it by 2. And again, then the time, this little t as a subscript, that is after that amount of time has elapsed, the concentration of A that you have left. So if we think about this process of undergoing half-lives, say we start with all reactant, we have 32 of the reactant. After the first half-life, 32, half of them would be gone, so we only have 16 left. So we have 16 of the reactant that is now left. That would be the first half-life. When we go to the second half-life, the absolute change is going to be different, right? It's still 50%. So what is left is then 8 of them, right? We had 16, we lose half of them, so we lose 8, and there are 8 left. So it's important to note that we're talking about the amount that a half-life is not, you're not describing how much reacts, but and actually a percentage. 50% are gone. If you start with more, 50% will be more of that. And you can have one half-life after the other. So you have a half-life, you have another half-life, the reaction keeps going, you keep losing more and more. But the absolute size of the decrease will be smaller, right? Because you think initially, say you have 1 molar, half of that would be after your first half-life, you have 0.5 molar. Well, now when you go from the first to second half-life, you're losing half of the 0.5 molar, giving you 0.25 molar. From there, we get to 0.125, right? The amount left keeps shrinking and shrinking. Keeps going down, and the initial amount is decreasing. So it's that relative change is what's constant between half-lives. So if we want to think about calculating half-life, there's time involved with it. We're always going to turn to our integrated rate law. So half-lives depend then on the order. So if we look at, say, something that's 0th order, A, we have our equation for the half-life, for the integrated rate law. So we can set, well, what would be there at the half-life? Half-life is this time where we have 1/2 left. And we know that if we set t equals 1/2, it would go, or t half, that goes in right there. We can define the amount that's of there at the half-life is based off the initial amount that's present. We can do some algebra, we can rearrange it, and we can end up with an equation that the half-life is going to be equal to the initial amount divided by 2k. So one of the things we said, short half-lives correspond to fast reactions. Well, if k is really big, k is in the denominator. So the bigger k is, bigger the denominator, the smaller the overall value of the fraction. So we'd get a shorter half-life. So that's consistent. When we have a first 0th order reaction, bigger k's lead to shorter half-lives. Very nice. We can do similar processes for 0th, first, and second order and obtain relationships for or equations for the half-life. One thing you will note is that k is always in the denominator for all of them. It doesn't matter. If you have a large value for k, that leads to a small half-life. Large k means a fast reaction, which would mean you have a short half-life. You will note that the initial concentration, however, either is present or is not. First order doesn't depend on the initial concentration, but it goes in different places. So we can see that initial concentration has different effects on half-life depending on the order. All right, let's look at an example of calculate half-life. Radioactive decay is a first-order process. The half-life of a polonium isotope is 138 days. What is the decay rate constant for this polonium isotope?
Okay, so I want a rate constant for a process, and what I'm given is the half-life. And functionally, this is a very common application of half-lives. One of the most common things we use for half-lives is to figure out order and then to determine the rate constant. It's an easier experiment to measure time than it is to measure rate, such a concentration over time. So we use this as a way to figure out information about a reaction. It's easier than using the whole big, the long process with initial rate methods and all that. Those are difficult experiments that then are hard to also even process. And so it's important that we know that this thing is first order, because half-life equations that we have are dependent or vary based on the order. So ln2 divided by k. So this is really important that's first order because we don't need to know that initial concentration then. And so we are all good there. So we can go ahead and do as if we want to solve for k, plug in everything else. ln2 is a number, so I have 138 days is the half-life is equal to ln2 divided by k. I do want to be careful. I'm swapping those out, so I get k is equal to ln2 divided by 138 days. Natural logs are unitless, but I get a value there, and when I divide that out, I get 0.00502 inverse days, or it could be 0.00502 1 over day. And so we've only seen rate constants that have seconds previously, but day is an acceptable unit of time. Generally, that implies you're dealing with a slower reaction. This reaction is relatively slow. It does take quite a bit of time to get up. To do this, it takes 138 days to react half of what you started with, or to have half of what you started with do the process, the nuclear decay process. And so, 0.00502 per day. You can really understand that in terms of reactions per day. Not a lot happens in a given day. But we can always use rate half-life to go back and forth, or to figure out the rate constant. That's one of the more common applications. Because you just measure a time, which is, use a stopwatch, relatively easier measurement than a rate. And so it's simpler, it's equipment. And then you can use that to figure out the rate constant, which is useful in general of describing the kinetics of a process.
In that example, we're looking at a first order process. And in first order processes, the half-life only depends on the rate constant, which means the length of time for a half-life is constant. So if you have a first order process, the first half-life takes a certain amount of time, second half-life, third half-life, they're all the same amount of time. When you're dealing with 0th or second order half-lives, the length of time for the half-life depends on the amount of initial amount of reactant that you have. So for a 0th order process, the second half-life is shorter than the first half-life, because your initial concentration is lower. So as the concentration gets lower, the half-life gets shorter. It keeps getting shorter and shorter because that initial amount is getting lower and lower. For the second order processes, half-lives get longer and longer. The second half-life is longer than the first, and the third half-life is even longer. What that means is you can again do an experiment where you measure the concentration of your reactant over time. We looked at fitting our equations to the linearized form of the integrated rate laws. You can also just measure half-lives. If the half-lives change, if the half-lives get longer, that means you're dealing with second order. If the half-lives get shorter, 0th order. If the half-life is constant, it's first order. In terms of using half-life as a value, the fact that they are constant for first order processes That's really the only place where a single number is actually useful, because that half-life is just a value. So that example was looking at radioactive decay. We look at the rates of radioactive decay using half-lives really frequently because it's just a number. It is a constant number that is always the same value. And so that makes it more useful in terms of actually describing the kinetics. Whereas for second order and 0th order, because half-lives depend on initial amount, they're not necessarily so useful. It is useful in the sense of, like, if you're talking about something like the availability of, say, drug, like a pharmaceutical in your body, if that is second order clearance or 0th order clearance, the half-life of that is really going to be useful, because you want to know how long it's going to take both before you fall below some threshold, say, of either effectiveness of the pharmaceutical or of maybe some danger level. You want to stay below, get below a certain level, or how much it's going to be in you, how fast for your body to get rid of it. So, but it's most common for first order. But this is a method that we can use to figure out order. Again, it's easier than doing initial rate method. All right, another video down. No questions for participation 9:15 in this video, but plenty more videos to go. See you in the next one.